First question is moment of inertia of a circular wire of mass m and radius r about its diameter is. Options are mr square by 2, mr square, 2mr square or mr square by 4. For a given circular wire or a ring which has the mass m and the radius r, the axis through the center is, suppose it is a z-axis, then moment of inertia about the z-axis will be equal to mr square for the circular ring. Now we consider two perpendicular axes in the plane of the ring. Say this is the x-axis and another one is the y-axis. Then using the perpendicular axis theorem, we know that Iz will be equal to Ix plus Iy. And because Ix will be equal to Iy because of the symmetrical distribution, we can write it is equal to I of the diameter. Therefore, Ix plus Iy will be equal to 2 into I of diameter. Therefore, from the equation number 1, we can write that Iz will be equal to 2 into I of diameter, that is the moment of inertia about the diameter. So, moment of inertia about the diameter of a ring will be equal to Iz by 2 and Iz is mr square. So, the answer is 1 by 2 mr square. Hence, option A is the correct option. Second question is two rings of the radius r and nr made of the same material have the ratio of moment of inertia about an axis passing through the center is 1:8. The value of the n is. The given rings are ring 1 and ring 2. Their radius are r and nr. They have the same material, so their linear mass density lambda is same and mass will be equal to, because mass is distributed along the circumference of the ring, so we can write mass is linear mass density lambda into length, that will be equal to circumference, so it is 2 pi r. This is the mass for ring 1 and mass for ring 2 will be equal to linear mass density into circumference, that is 2 pi into nr. So for ring we know that moment of inertia is m into r square. Mass of the first ring is lambda into 2 pi r and radius square. And I2 for the second ring will be equal to mass is m2 into r2 square. It will be equal to lambda into 2 pi nr into nr whole square. We have to find the ratio of the moment of inertia which is given. This is I1 by I2 is equal to lambda into 2 pi r into r square divided by lambda into 2 pi into nr whole square, and this ratio is given 1:8. This implies that this lambda get cancelled, 2 pi get cancelled, and we have r cube divided by n cube into r cube, and it is equal to 1:8. R cube also get cancelled. This implies that 1 by n cube equal to 1 by 8 or n cube equal to 8, that is equal to 2 raised to power 3, hence n equal to 2. Option A is the correct option. Third question is, a thin wire of length L and uniform linear mass density ρ is bent into a circular loop with center at O as shown. The moment of inertia of the loop about the axis x dash is. In this question, the length L is equal to the circumference of the loop. So we can write it is 2 pi r, where r is the radius of the loop or the ring. Therefore, we can write radius is equal to L by 2 pi. In the figure, first we will find the moment of inertia of the ring or the loop about the z-axis, which is perpendicular to the plane of the ring and through the center. So we can write that moment of inertia about the point O, it will be equal to total mass m into radius, that is r square. So we can write, because mass density is given rho, so it will be equal to rho into length of the wire, which is L, into r square. So we can write it is rho into L into, we will convert this r into L, so we will write it is L by 2 pi whole square. So we can finally write it is L cube by 4 pi square. This is our equation number 1. Now we will find the moment of inertia about the axis through the center and in the plane of the loop. So this axis is suppose x-axis, and here it is perpendicular axis is y-axis. From the perpendicular axis theorem, we can write that Iz is equal to Ix plus Iy, and Ix will be equal to Iy because of the symmetrical distribution of the mass around the center. Therefore, we can write that Iz, which is Io, is equal to 2 into Ix, or Ix is equal to Io by 2, and it is equal to rho L cube by 8 pi square from the equation number 1. So this equation becomes second. To get this equation number 2, we have used the perpendicular axis theorem, which is given as Iz is equal to Ix plus Iy. Now to find the moment of inertia about the x dash axis, which is the tangent to the loop, it will be equal to the moment of inertia about the x axis plus mass of the ring into distance between these two parallel axes, which is equal to the radius of the ring. This is the parallel axis theorem. So we replace the value of Ix here. It is rho L cube by 8 pi square. Mass of the ring M is rho into L, and radius from the formula, this is L by 2 pi whole square. So this will be equal to rho L cube by 8 pi square plus rho L cube by 4 pi square. On simplifying it, we will get it is 3 by 8 rho L cube by pi square. Hence option D is the correct option. Fourth question is, a thin circular ring of mass m and radius r is rotating about its axis with a constant angular velocity omega. Two objects, each of mass capital M, are attached gently to the opposite ends of a diameter of the ring. The ring now rotates with the angular velocity omega dash. In first case, it is the ring of mass small m and has the radius capital R, and it rotates with angular velocity omega. So we can write that in this first case, moment of inertia of this ring about the axis through the plane perpendicular to the plane and through center, which is a z axis, is m into capital R square, and its angular momentum will be equal to I1 omega 1. It will be equal to m into r square into omega. This is our equation number 1. In second case, if there is a mass bodies at the opposite ends of the diameter, small m is the mass of the ring, and now it rotates with angular velocity omega dash. So moment of inertia in second case will be equal to moment of inertia of the ring, this is m into capital R square, plus moment of inertia of the attached bodies, and these are m into r square, where z axis is the axis of rotation, plus capital M into r square. So it is equal to m plus 2 capital M into r square, and omega 2 is omega dash. So we have to find this omega dash, and moment of inertia we have calculated. Therefore angular momentum in second case will be equal to I2 omega 2, and it will be equal to m plus 2 capital M into r square. This is the moment of inertia into omega dash. This is equation number 2. Because the objects are attached gently, so there is no torque. Because torque is 0, therefore angular momentum will remains conserved or constant. This implies that L1 will be equal to L2, or we can write m into capital R square omega will be equal to m plus 2 capital M r square into omega dash. Therefore omega dash will be equal to m r square omega divided by m plus 2 capital M into r square. This r square get cancelled, so finally it is m by m plus 2 capital M into omega. Hence option D is the correct option.